Bismillah ar-Rahman ar-Rahim. Good morning, everybody. My name is Magdi Matkour. I'm professor at Ain Shams University, and I have the pleasure to be with you on this session. Today, we are going to tackle a subject that relates to how biotechnology can assist. And the title of this session is Waging War on Hunger. I have the privilege and honor to be a member of this panel of two eminent speakers, two pioneers in the field of biotechnology, if not the pioneers of this field, Professor Van Montagu and Professor Potrikis. I have the pleasure to present you today to present your views about the subject. We'll start with Professor Mark Van Montagu, who is the president of the European Federation of Biotechnology, and he was full professor and director of the Laboratory of Genetics at the Faculty of Science in Ghent University and scientific director of the Genetics Department at the Flanders Inter-University Institute for Biotechnology. Together with his colleague, Professor Jeff Shell, Mark Van Montagu discovered the gene transfer mechanism between agrobacterium and plants, which resulted, as you very well know, in the development of methods to alter agrobacterium into an efficient delivery system for genetic engineering in plants. He developed plant molecular genetics, in particular, molecular mechanisms for cell proliferation and differentiation and response to abiotic stresses. Professor Van Montagu received numerous outstanding awards for his pioneering work, including the prestigious Japan Prize. He holds 6 doctor honoris causa degrees. In 1990, he was granted the title of Baron by Baudouin, first King of the Belgians. Professor Van Montagu, I have the great pleasure to introduce you for your speech today.
Good morning, and thank you for the kind introduction. And sorry that I didn't give the title of the talk, so finally I choose agriculture and forestry in the omics area. You heard a lot about the omics already in the last days, and I think it's important that we see how fundamental science can help the enormous challenges we have ahead. If we look at plants, if we look at our planet, we have to realize that it's rather recent, at the end of the 20th century, that societies really became concerned on the damage that we are doing on the planet. We see that all over, these landscapes that we appreciate and love so much are disappearing. People who know Malaysia have known it in the 50s or the 60s. Well, we'll not go back too far. They knew the tropical forest that was there. Everything has been chopped down and is now rubber trees, oil palm trees. Indonesian is following. Many places in Africa and Latin America are systematically, day after day, the fantastic trees are chopped. And that's what society is doing. And what can we do? Well, we have to mobilize each other, that we try through our knowledge, through science and engineering, that it would be applied to technologies, that we can do agriculture on the arable land that we already recuperated from nature, and that we don't go on. And the green movement, who is now so adamant against genetic engineering, should realize that if what they claim they want to be friends of the earth, that you only are friends of the earth if you can bring solution to save what there is still possible to save. And I think at the moment, it's really the last chance that we have to apply science and engineering. We really must balance the future demand against sustainable agriculture, sustainable supply. And we have to see that with the population monster around, like it has been quoted several times here, that we double our productivity, but that we do it in a sustainable way. And that we bring all over where there is agriculture, that we bring the knowledge that is already existing, how to do the best of the techniques that we have in agriculture. But most of all, that we use our science that we have worked out in the faculties of science, and that we bring the new plants to the field, and that we start a sustainable production, and that we see that we are ready for the climate instability and for the further damage that we anyway will do. So we have to, not only in our engineering systems, in our industry, in our society organizations, reduce waste, but most of all, learn how to recycle. So we have to find the enzymes. We have to construct the enzymes in organisms that we can use agriculture waste, city waste, to make new sources of material for our industry. Because what's it around as natural resources is not only what we traditionally used as chemicals in the soil, but it is most of all what agriculture, what plants can bring us. And that we have to learn to use. And science can do it, but the real bottleneck we will see is everywhere the governance. Till now, the hunger problem, people who know tropical agriculture know that it is not because there is no supply from food that comes from the rich countries, but because we never really cared to bring the existing science and the existing technologies to the places where they're badly needed, that there would be a better yielding agriculture. Notwithstanding the efforts that CGIAR has done, it's the local governance, it's the political approaches that have been lacking, and that we have to repeat. Luckily now, people realize the urgency, and we are happy that, particularly in the UK, the chief scientist, Lord Beddington, has now already several times made reports. They are a bit long, 350 pages. Executive summary is nearly 40 pages, but people should follow it, learn it, spread it. You can find it on the web, with the need more money for agriculture, more attention for agriculture, more scientists joining agriculture, more scientists using the techniques that are available. That is the only way out. And thanks to the UK and some Scandinavian countries, we can present to society what is possible, but we have to see that it is followed. And unfortunately, the European Union has still not found the way out to go ahead, and we all have to unite to go on, to stress this possibility. Talking about the population monster, people go on laughing, and we see it often in newspapers, on these arrogant intellectuals that impose themselves and say what Malthus was saying. We know that Malthus was not right, and it's 300 years later he was not right. That's what they quote. Unfortunately, we know that Malthus was very, very right, and that at the moment the situation is really dramatic. We in the civilized world, we think still that we can ignore it. Human optimism can be dangerous. We say that we were able till now to cope, so since till now we were able, it will go on. But if you do the hard calculations, the situations are different. We have to realize that in the beginning of the 20th century, we were 1 billion. After World War II, we were 2 billion. 50 years later, we tripled. We were 6 billion. Now we passed 7. We go on merrily to 9 and 10. What the responsibilities to make a society and that we can cope with the pollution. It's not only feeding, it's really the destruction that we do to the planet. Ecological systems, they look good and then suddenly they collapse. And we know that it will happen with the planet, so that's what we are responsible for, to find solutions for that. So when I'm talking here, it's because indeed in the 70s, by doing fundamental research, like all people in Faculty of Science there, we were intrigued why a soil bacteria, Agrobacterium tumefaciens, known since the beginning of the 20th century, why it was making tumors on plants. And we could show, and we, that, as has been said, Jeff Shell and myself and our co-workers, we could show that in nature, genetic engineering is going on. And now we will learn that there are many more bacteria who bring information and signals to eukaryotic cells, but we can come back to that. But there in the 70s, it was really mere genetic engineering. This bacteria is able to transfer its own DNA in a plant cell. The plant cell, at that moment when this DNA is expressed, starts proliferating, synthesizing odd amino acids. It's condensations of keto acids and some amino acids. And these compounds called openes are a source of carbon and nitrogen for the bacteria. So that's the ecological reason why the bacteria does it. It forces a plant to make compounds that Agrobacterium only can use and that other bacteria cannot use, fungi cannot use, and the plants cannot use. And it's the moment maybe already to stress that in general, plants secrete 25% of the photosynthate on the form of sugars and amino acids in the environment to attract bacteria that protect them, and they know very well, and now we start realizing that it is for all living beings that they grow together with the microorganisms. And this microorganisms plays on it and creates a niche for growing, and the way to do it, and that's what we could show, that it harbors a large plasmid, 200,000 base pairs. In those days, it was not very easy to identify such very large plasmids. People were the habit in the 60s to learn about small plasmids with antibiotic resistances. These very large, sometimes called catabolic plasmids, exist a lot in bacteria, and the gram-negatives move around, and gram-positives, sometimes you have linear plasmids. All that is very interesting science, but the breakthrough was when in '74 we could show that this plasmid exists, and in the years afterwards that a segment of that DNA is copied in a single strand attached with all proteins that are already there in the bacteria. Evolution made it, and it then transferred to the nucleus of a plant cell, and that's the engineering that goes on. So at that moment, for us, it was sure that if nature does this genetic engineering in that simple way, quote unquote, that we would be able to replace the genes that makes this tumor and these compounds, and replace it by genes that were interesting. And that's the saga of Agrobacterium, and that's the method that was for the first time demonstrated to function. And exactly, it was can say 30 years ago. It was in the Miami Winter Symposium, 1983. So next year it will be 30 years that several groups showed that you could then express a gene, and it was a marker gene, kanamycin resistant in plants. And then the adventure could start, and at that moment we immediately were able to take some interesting genes, the genes from Bacillus thuringiensis, to have the insect tolerant plants. We could make herbicide tolerant plants. We could engineer male sterility that was the success of the years 80, and that's why the group in Ghent at the moment still is a fantastic concentration of a laboratory of 300 people, with as director my successor Dirk Inzee, and that we are still ranked among the top of fundamental plant science. But that doesn't help the planet. Fundamental plant science is essential, but we should be able to apply it to make products that our planet badly need. For the fundamental science, we were happy. Chris Somerville, Ilyot Mairovich, and quite some scientists all mobilized so that the scientists would focus on a model plant, Arabidopsis. And there, very rapidly, plant molecular biology came alive. All the essential genes in plants were cloned, became available. International consortium did the sequence. We have data banks for all that have a hard time sometimes to survive and to find finances, because not everybody realizes how important this science is. But at the moment it worked, and it still works, and hope that the finances will be there, that we can continue. And in around 96, the commercial plants, the transgenic plants with interesting traits became commercialized. I take a symbol here, cotton, because at the moment 70% of the cotton production is already transgenic cotton. Cotton is important for Egypt, and that's clearly accepted everywhere. For food, people tell still fairy tales that about to frighten people. We can come back to there, but there also we have badly need much more than only corn and soya beans and some rapeseed, and more will come. But thanks, the first steps in these 30 years was making plant molecular biology spread an activity that was done in all countries over the world. And it is building up knowledge, and that's what's going on. And now we talk about systems biology, since we are already dreaming that if we see a plant, that we will understand the pathways that are acting in growth and development, in the biosynthesis, and that we will know the regulations of the pathway. We need it, but meanwhile we cannot wait till the science, because it's the same in the medical field. What we know and what we will know in 10 and 20 years is very, very different, but we have to go ahead. So for the plants, we also have to go ahead. Luckily, at the level of the genomes, progress is good. You have heard Wang Mingyang talking here, and he talked about what the Beijing Genomics Institute is doing, and everybody likes to collaborate with them because we badly need these genomes. And it is not only the genomes, but also for the RNA sequencing, and most of all for the methylomes, the areas that are methylated, because meanwhile we rediscovered epigenetics, the importance that under stress conditions the chromatin unfolds, new genes are switched on, DNA becomes methylated, and these structures are passed on after division to the whole of the somatic cells, and in some cases probably also it can go some generations further. So that's new, and that's what we also have to do, the sequences, and link them up to the phenotypes. And that is what is going on, and that's the fantastic science that is a pleasure to be part of and to continue, and that we have to convince the younger generation to follow. And I can say that all over the world, these genome analyses go well in the medical field, and we see new startups like Biotech that probably none of you know. It's a startup that's now in Belgium, but actually started in Lausanne, and with the help of Philips Eindhoven it was developed. And it came from an observation in the medical field that classical clinical analysis that you all do when there are some health problems, they are still the same enzyme tests like long time ago, 10, 20, 30 years ago. Well, some ELISAs are there, but it's the most of the molecular biology that medicine already has really substantiated and see what role it plays is not used because it's too expensive to study gene expression. You cannot do Affymetrix. Well, Biocartis developed systems that probably for €1 or €2 you can analyze 40, 50 genes. And of course, that's important for plant breeders. That will be the base in the future for what we call green Biocartis. That's the company that probably will start next year in Belgium, I hope. But at the moment, they are based there, and this Biocartis is together with Philips Eindhoven developing already the instruments for the medical field, so we are waiting. The same mass spectrometry is now becoming available. It's analyzing for all the metabolites in the tissue, sometimes in single cells. It helps for the protein analysis. So that gives an enormous link for understanding phenotypes, for studying the proteome, and for do metabolomics, understanding all the compounds, the biosynthetic pathways, so crucial for the further study of plants. But with all that, all these outstanding developments, all this omics technology, yes, we have an explosion of information. But we have to realize that the best that the public sector can do, the best that our universities can do, is create knowledge out of this information. That's essential first. But afterwards, applying this knowledge to make products, that is what our planet needs, that's what our society is wanting. That's the private sector that do. And there, with all these over-regulations, all these fear stories that have been spread, all these well-intentioned people that are fighting GMOs, it's catastrophic. Because if there is no easy way to apply this knowledge, financial world will not follow. And it's discussions for other sessions, but it's crucial that industry not only take some niche markets and make a lot of money with these plants, it's all the plants that we need to improve for all the different tasks that agriculture is doing and bringing benefit to the planet and trying to solve the enormous needs we have created with this overpopulation. So this sector of plant genetic engineering, GMO commercialization will only have success if we can present to society useful products that we know that we can make, but that we only can make with the help of industry, with the help of the financial world, and then we will convince society. And as long as we cannot do that, Greenpeace will be successful in blocking the science, and they will be successful in doing enormous damage to our planet. So, once more, plant biotechnology is not important for food and feed production alone. The cutting-edge science goes very well, thank you, but it's the applications we have to realize. Our industry is waiting to new raw material that they can efficiently use because petroleum becomes more and more expensive and will become scarce in the second half of this decennia. Pharmacy should be affordable for everybody, should not be only for the rich. So there is possibility probably by detecting a lot of compounds and overproduce them in plants by producing proteins in plants to make it much cheaper. Of course, pharma industry will laugh with this naive scientists. They know that it is not the cost that is important, it's all this over-regulation. Well, if you do it together with developing countries out of plants, sure, there will be ways to find it, the regulation, to do it in a cheaper way. And it's only the will to go ahead and the need. But that's we have to do together with the developing countries. And that's why scientists in what we call still the Western world, the rich world should urgently work together with the scientists in the developing countries to do on that spot the development also for the pharmaceutical industry, not only for food and all. And most of all, of course, the pollution that we have done and that we are ongoing doing, we really have to find solutions, and plants can do that. But if we talk solutions, it's not only innovative biotechnology. We have to use the best of knowledge we have in agriculture. So the plant breeders, we have more respect for plant breeders. Developing countries should make seed companies, because most of the seed companies have been bought by the multinationals. So we have to have good extension services. Public sector should make them available. At the moment, the extension services are done for the products made by the big agrochemical groups that have bought the seed companies. More should be done, and at that moment, agriculture will progress in the developing countries. So it's a good collaboration we need between our schools of agriculture and our faculties of science. And in very few places that happens. And that's a responsibility we have. So in my talk, although I was long in my introduction, I want to talk about science and science communication. We know that we have to make sustainable agriculture. And I want to stress already how important aquaculture will be, because the sea is an enormous surface, and we know that there are a lot of interesting compounds can be made by macroalgae. And the Chinese have already done enormous work, and it's very beneficial for the sea, because all the products that fertilizers that are not used by the traditional plants and that used in agriculture and go to the sea, and some places give areas of anoxia, and all the fish die. That's what you see in the Gulf of Mexico, in the Baltic Sea, along the coast of France and the UK. But the Chinese, by making macroalgae culture, have made that the macroalgae take it, proliferate, and make that there are areas where there is oxygen, and that the sea is healthy. So altogether, agriculture, aquaculture, we have to use the best of science, but we also have to make a less polluting industry. We have to make natural resources, the agriculture waste, all the novel plants that we will engineer. And that will only be possible if we do good communication about what science is. So in the first place, want to stress once more that the ecosystems are so important. The enemies of GMO say, we will do agroecology and we will solve it. No, you need to do good science, and then you can solve it. And you have to use molecular biology to study ecology and to study all these interactions. And then you know how you will be so successful with your future agriculture. And we learn that all plants, just like all animals, that all eukaryotes grow in very, very tight symbiosis with microorganisms. And with metagenomics, we can now analyze mixtures of thousands of microorganisms. Not the full genome, but 2/3 is sufficient. You learn about so many genes, and they will become available. You study ecosystems, you will learn. So we talk now about the hollow genome concept. And this hollow genome, we start having the tools to study it. We have to study it. It's wonderful science, and it will bring a lot of solutions. But we have to explain to society what we are doing, because now we are in a very difficult situation in the world of communication. We have to see that we find solutions for the arid areas, because there are many. So can we reconstruct topsoil that has been eroded? What have we to do? Which type of plants we have to, and microorganisms we have to have first? How can we make such a whole system again? For the plants that are already adapted to harsh conditions? Can we engineer them for having higher yielding? Or should we, the high yielding corn and wheat that we have, engineer for drought resistance? Or both at the same time? That's challenges that scientists in the Faculty of Science should do with the schools of agriculture. And most of all, we should learn that there are quite some interesting plants around that have never been studied, like Latyrus. It's a leguminous plant. Many thousand years ago in Egypt, you knew very well about Latyrus, because in the tombs of the pharaohs, you find the seeds of Latyrus, because it was called the wonder plant. This slide of Ethiopia, in its high drought that even chickpea cannot survive, Latyrus is still green. If there are floods in Bangladesh, 3 weeks water retrieves, plants have a possibility to grow. The first there is Latyrus. Latyrus survived, can stay 3 weeks without oxygen. This plant is not used, although it's nutritious, because it has toxic compounds, a toxic amino acid. By itself interesting, because it works on the motor neurons of the lower limbs. Normally in medicine, we don't know a difference between the motor neurons of the upper part of the body or the lower part of the body. So it's an interesting compound that's there. So we should have able to raise money to study it and to try to remove it and to make it as a useful crop because of these properties. And there are many other unused crops that deserve. Other solutions that biotechnology has already brought. It has been talked in other sessions, the Phytophthora-resistant potatoes. We have seen in Ireland, but all over Europe, also north of France, Flanders, even Poland, how in 19th century, when the potato disease was there, how strong the famine was. People say, you just have to do the breeding with some Andes potatoes, and then you will make in a natural way resistant potatoes. It has been done. It takes 35 years to cross in 1 or 2 genes. They exist, but people want the benches or the varieties désirées that industry is using here that people are habit of eating. And the scientists have already identified 17 genes, so batteries of 5 or 6 genes can be made. Has been done. Last year we did the field trials, and very well-intentioned people were mobilized by pressure groups and non-governmental organizations to destroy it. And it's that same happened with Jonathan Jones' potatoes. They have a heart attack even in the UK. So we have to explain to society that there are very interesting products ready. It's still not the wonder strawberry that of half a pound and that has a fantastic taste. That doesn't exist yet, but I'm sure it's possible to make. And that's the responsibility we have that it has. But we also have to realize that how difficult the way is to explain it to society. By example, in Europe, 3 companies did a major effort to use agriculture waste. Because we have seen with sugarcane how Brazil is able to make high yield of alcohol and how they can use alcohol as biofuel. Our industry would like also that agriculture waste be the source of raw material for all the chemicals we are making that we can switch. If that would happen, then it would be possible to replace gasoline. Well, Novozymes and Danisco in Denmark and DSM in the Netherlands have worked by genetic engineering to make organisms that already could replace 62% of the import of gasoline in Europe. By making stations to do that all over Europe, it would create 1 million jobs, bring in 31 billion euro, and we would gain another 40 billion euro by not buying gasoline. That's the Bloomberg report of spring 2010. So that looks fantastic. European Union says, well, it's genetic engineering, we have to be careful, and we will not give the subsidies, we will see, we will not help this to develop this industry just like any novel industry that asks for subsidies. What has happened? Novozymes and DSM took all these projects to the United States. And there, it's a big success. Took it to China. Danisco was bought by Dupont de Nemours and also uses it in the States. So, if we don't fight our way with society, that's the hurdles we have at the moment. And Europe has to realize that more and more, if they don't help the bioeconomy, if they don't help the applications of science, that they will be in the class of the emerging countries like Brazil and China. Still, you're interested more in science, maybe, just to say that we made transgenic poplar trees that can grow much denser even like that, can nearly grow it like corn and then harvest it after 4 years. So there's never any pollen that flies if people would have objections to that. But these poplar trees make modified lignin. That's interesting for industry, but most of all, the cellulose is easier to separate. And of course, that's only a first step. These poplar trees will be used as raw material for industry with quite some improvements. But again, all these plantations still don't have the authorization to be used for industry. That's a fight that has to be done. Other plants are developed. The genomes are done for castor bean, for jatropha, sweet sorghum, some grasses like miscanthus that will be the plants for the future, for the industry, for animal feed. And there is no way out. We will need it. And that's the agriculture in the future we'll see will happen. So in summary, if people say the scientists, they will destroy biodiversity. No, at the moment, we have made the tools to study biodiversity, to capture the value of biodiversity. So industry should help us to protect the maximum of biodiversity, because that's what the scientists did. We can use the pathways and use it in other plants on the areas in greenhouses, because sometimes you don't need very much, or in a limited number of fields as an interesting product for our farmers to have a high-yielding return from their agriculture. That's what science can do, and it's further developing. So now, talking about science communication. Society doesn't make the right decisions to promote this science. And we have to understand it. We have to see that our brain in the evolution came over the 10,000 and 100,000 years that we didn't have science. Science extremely recent. Many of the science, we talk about decennia. So it's logic that we have had to survive and take decisions with other defense mechanisms. But we have to realize that we have a habit of belief systems. And it's the basis of research. A scientist, if he do some observation, he starts believing. But then is the scientific method. And that is our duty to communicate to society, and surely to all the scientists and to all the students, that the scientific method is the only one we can rely on. That is, you do observation, do a hypothesis, do experiments to challenge it. Either it's confirmed or not, either the theory is wrong or you forgot something, and then you can go on. And if it's positive, then you can go further. So at each moment challenged. Science is not a belief. Science is not a dogma. Science is something that is challenged at any moment by anybody, and then there is a consensus and a peer review, and that's the only point we can be sure of. And we have to realize that if you don't do that, you fall in all kind of patterns, and then emotionally you want to you see only observations that enforce your beliefs, and there we have to do an effort of discussion. And we shouldn't laugh, because so many people believe in ghosts, in extraterrestrials that visit, or that they talk to their parents or great-parents. It's good for society as an individual to give you courage, but don't make it a law that which you would forbid something, and especially science, to happen. That was the worst what can happen to a society. And I can assure you, we have to have the responsibility to understand that people have these beliefs. Nobel Prize winners, the person who developed PCR, Nobel Prize Chemistry 93, believes that UFOs come and communicate here. Okay, it's funny, it's amusing, but if it doesn't have special consequences, it doesn't matter really our society. So we have to be able, knowing how we make trusts and how we can progress in science, that we communicate to the society that they'll know. With all the GMOs that we have made, all the laboratory work that we have done, there is never any adverse effect that has been reported from GM crops. A lot of stories circulate, but they all have been proven false. But they go on. People believe in the monster of Loch Ness. And if you go, all the proofs you can do, you cannot say that you prove that the monster of Loch Ness doesn't exist. You can say, we went with bathyscaphe there, we used sonars, we did that. If people want to go on to believe in the monster of Loch Ness, it doesn't harm. And it's a nice fairy tale. But if it really blocks the development of science, and it blocks the tools that we need to have for our agriculture, then it's a problem. The same for environment. Many positive effects have been reported on the toxins from fungi that are no longer present if you have less damage from insect with the BT plants, and so on and so on. Never an alarming scenario has been seen. Sure, the genes fly around, but okay. We have to realize what is going on. What is nature really? It's 10,000 years that we do genetic modification. None of the plants or animals that we use in our agriculture system, in our food system, is the same natural animals or plants that were found in nature. We always have improved because we have been so reckless to be with so many people on our planet. But what is a classical genetic modification? Well, if you have a desired gene in a genome, you cross it with already an optimal variety, and then you exchange, but you don't exchange your gene, you exchange many, many genes. So then you have to cross back till you only have the one that you have introduced. And that takes a long time, is expensive, and is very limited, the way you can do it. And often you start using your plant having lost quite some interesting traits. In biotechnology, you just take your gene and you insert it. So that's the science, and we have to communicate it. But there is, of course, a problem. At the moment, the commercial applications is done only in what we call hybrid crops. And then people say, oh, these GMOs that the companies are selling, the poor farmers cannot use these seeds again. That's nothing to do with GMOs. It's just because it's done in hybrid crops. And hybrid crops are important because they are only ones that give very high yield, are better disease resistant. They have been introduced for corn at the end of the 30s. It saved in the United States the country in the Big Depression by booming the agriculture, and it was the Minister of Agriculture of Roosevelt, who was also then the director of the company Pioneer, who started it, and since then a lot of hybrid crops have been used, and seed industries, that's the only one they commercialize. If you want to have it in other crops for vegetables and so on, well, you will have to negotiate with the public sector how to, and that's what Embrapas in Brazil does, how to bring other seeds to the farmer. But that's discussions for other groups, what type of agriculture and intensive agriculture can be developed. And the fact is, we can only have high-yielding agriculture through hybrid crops. So a lot of GMOs in the future will always be made in hybrid crops. It's then the good governance that has to make that the price difference is not too high and that it is acceptable and that the farmers can use it. But that's nothing to see with GMOs. GMOs are unnatural. Well, we have to see what is nature. The whole world is a genetic laboratory. There are not stable genomes. All genomes always have to adapt. It's the basis of evolution. Life would not exist if there was not this permanent adaptation in a genome. Even in our lifetime, if you are interested, read the Scientific American of last February. In our brain there are movements, there are elements that jump around under stress situations because our neurons have to adapt into certain conditions, and it seems that they're also. And the genomics techniques have shown that for all the organisms that at each moment under stress situation, movable elements make that there are new genes expressed. So it's absolutely natural. And it is absurd to talk about human gene or pig gene or rat gene. All these are the same big collection of genes that have been used in evolution. And we are studying them, we learn them, and we just alter them and adapt them to make the products we need. And it's very sad that then these organizations start telling nonsense and mobilize and misuse the beliefs of persons. We have seen that in Austria some years ago, a scientist thought that he saw that mice were, when they feed them transgenic corn, had less offspring. And then immediately the government, even the scientists didn't publish, but the government who knew these results advertised them and announced them. In Europe there was not too much talk about it. Greenpeace knew that it was nonsense, but so they didn't dare in Europe to make a lot of fuss about it. But in India, friends show us this, and in Africa there was the stories that if you eat GMOs, you will become sterile. And the banners are there, signed Greenpeace, and that can only say criminal to do that to persons who are not informed about what science is and mobilize them in that way for a cause. And that's what we have as scientists to realize, because the threats are there. We have these microorganisms that destroy our agriculture. We have plants that are not nutritious enough and that we know we can improve, and Ingo will talk about that. There is so much starvation in the world, so much dramas, so much empty stomachs that are the basis of damage to our society, to what mankind has done. So it's our importance that we use this science, and we have to realize that we can do it and that we will do it. But it's important for our planet that we do it now instead of doing in 50 years, because then we will have been some billion more and so much more damage will have been done. So it is our task, if we know that we can make a better environment, to do it and to mobilize all our colleagues in ecology, in other sciences, to all together to explain to society what is science, what can science do, why do we need science, and then we can progress with plant biotechnology. We cannot wait, we say, so we have to do it and discuss here, by example, in Alexandria, how we can organize, we can unite each in his discipline to bring this progress, because the planet badly needs it. Thank you.
Thank you very much, Dr. Mark van Montagu. Our next speaker is Professor Ingo Potrikes. He's a professor emeritus at the Institute of Plant Science of the Swiss Federal Institute of Technology in Zurich. Dr. Potrikes obtained his PhD in plant genetics from the Max Planck Institute for Plant Breeding in Cologne. And he was the research group leader at the Max Planck Institute for Genetics and the Landberg Heidelberg, and also a research group leader at the Friedrich Miescher Institute, Basel, Switzerland. He was full professor in plant science at the Swiss Federal Institute of Technology from 1986 to 1999. His work included contributions to food security in developing countries, focusing on development and application of genetic engineering technology for and to food security crops, such as rice, wheat, sorghum, cassava, etc. In addition, he focuses on problem of disease and pest resistance, improved food quality. He is the inventor of golden rice, as you very well know, and chairman of the Humanitarian Golden Rice Board and Network. Dr. Potrikes received several awards and distinctions, and also obtained an honorary doctor from the Swedish University of Agricultural Science in 2002, and the University of Freiburg, Germany in 2007. He was listed among the top 100 living contributors to biotechnology, and also was considered to be the most influential scientist in the area of agriculture, industrial, and environmental biotechnology for the decade of 1995-2005. With this, I'd like to introduce Dr. Potrikes. The floor is yours.
Good morning. Thanks to the organizer for inviting me to come to BioVisionAlexandria again. I will focus on one example only, and I decided to respond to questions which I got from the organizers. And I will show you the questions, and the answer to these questions will be the topic of my presentation. How long did it take to develop golden rice? And how long did it take to get it out to the people who need it? Where is golden rice being distributed today? How do you see the future of biofortified crops in the coming years? And what are the lessons learned that will be beneficial for the biofortification of other crops? So, these are my topics, but before I can start to answer these questions, I should give you a little bit background information about golden rice, because I'm not assuming you may have heard of it, but you may not really know too much about it. So, what is golden rice? Why was it developed? And how was it developed? We started off to try to develop not golden rice, but a rice which would contain provitamin A, because we were concerned about the problem of vitamin A malnutrition, which is an enormous public health problem worldwide. Rice is the major staple food crop for nearly half of mankind, is a fantastic storage for calories, but is very poor in micronutrients. And one of those micronutrients which is missing is provitamin A. The consequence from the situation is for poor people who cannot afford to buy a diversified diet, the fact that despite enormous efforts in trying to use traditional interventions against this deficiency by, for instance, distributing cost-free vitamin A capsules, the WHO is investing every year between $90 to $100 million in this intervention. We still have 400 million rice-dependent poor who suffer from vitamin A deficiency. And the consequence from this deficiency is that it impairs vision, the epithelial integrity against infections, the immune response, hematopoiesis, skeletal growth, and so on. And the consequence from that is that we have every year about 500,000 blind children as a consequence of vitamin A deficiency, and about 2 million deaths, mainly children. So we felt we should try to use the power of science to develop complementary interventions to the existing traditional ones. So the idea we were following was, let's try to use science to develop a rice plant which contains vitamin A. Well, no plant contains vitamin A. Plants produce provitamin A, which our body converts into vitamin A after ingestion. So the challenge was more precise, how to get a provitamin A rice plant. Well, there were 4 basic alternative possibilities. Rice plants have provitamin A in all green tissues, except for the starch-storing tissue we eat. So the rice plant has decided somewhere in evolution to switch off the pathway leading to provitamin A in the endosperm specifically, and that's understandable because the rice plant has no advantage of producing provitamin A in the starch-storing tissue. So the first approach would be to try to find in the natural variation of rice and all rice relatives a plant with a yellow endosperm because provitamin A gives tissue a yellow color. This has been done intensively by rice breeders all around the world. The rice breeders wanted since long to develop a rice plant containing provitamin A because they knew about this problem of vitamin A malnutrition. And the rice breeders had looked at all possible natural variation in all rice accessions around the world, including all relatives of rice, and they couldn't find anywhere a rice plant or a rice relative which would contain a yellow endosperm. At that time, the rice breeders learned about genetic engineering. And they said, well, you genetic engineers, why don't you do something sensible and develop a yellow endosperm rice plant for our purposes? And our project was responding to the wish of traditional rice breeders to try to provide them with the necessary variations that they could start a breeding program. Well, if you try to do so with the help of modern science, you have 3 possibilities. You could try to approach this goal. The most immediate idea was to apply mutagenesis. As the rice plant had somewhere switched off the pathway, you could hope that through mutagenesis you could switch on the pathway again. So there were enormous mutagenesis projects around the world, using all possible mutagens, including Arabidopsis as a modern mutagenesis. But up to now, mutagenesis has not come up with a yellow endosperm rice plant. Well, in 1991, when I had appointed a PhD student to work in my laboratory on this idea of engineering the pathway into rice, I felt I could need some financial support, and I applied to the Rockefeller Foundation to help me with this idea of engineering provitamin A into rice endosperm. And the Rockefeller Foundation did not just say no, but they organized a so-called brainstorming meeting in New York, inviting 30 of the best-known biochemists of the pathway to discuss the project. And the result of this brainstorming was the opinion that if somebody wants to do what we wanted to do, it would be crazy to try to engineer the pathway because it was far too complicated. It would be far better to try to find the switch with the available molecular techniques and with the basis that in maize people had found such a switch. So the general opinion of the expert group was that a program should be financed which was looking for the switch to turn on the switch again. This project has funding since early 1992, and this project has not found the switch yet. To everybody's surprise, because everybody was convinced this would not be too difficult. So we, at that time, felt we should, despite all difficulties, try to work on engineering. And we received some modest funding from the Rockefeller Foundation, one postdoc in my laboratory and one postdoc for the laboratory of my partner, Professor Peter Bayer, who was a biochemist of the program. Well, if I show you the pathway, you may understand why nobody wanted to believe and had good reasons that to engineer this pathway into rice endosperm was a bit far-fetched. We would have to be prepared to isolate and introduce 8 genes, hoping that all these genes would cooperate and hoping that the cytology of the endosperm cells would cooperate and provide storage space for provitamin A if provitamin A would be synthesized. Well, there were hundreds of good reasons to forget about this idea, but fortunately I was stubborn and we worked for 9 hard years. And at the end, it was possible what nobody was able to believe 9 years before. It was possible to engineer the pathway into rice in such a way that the rice endosperm now is yellow. And it is yellow because it contains provitamin A. Well, I would like to stress very clearly, we were fortunate. The chances that this project would have failed were definitely 1,000 times higher than the chances that the project was successful. And in part, we were fortunate not only that the endosperm cells were cooperative, but also that the number of genes we had to engineer became smaller and smaller in the course of the project. If you remember that at the beginning we had to consider 8 genes, we can now engineer the pathway in a reproducible fashion, and many people have done so with 2 genes only. And this is thanks mainly due to the fact that one soil bacterium has, during evolution, developed one gene which fulfills the function of 3 plant genes. And thanks to the surprising fact, which was only visible after we were successful, that the first 2 genes, E1 and E2, or the enzymes, the genes for these enzymes, were active, which was not visible because there was no result from this activity. And the lycopene cyclase 7, 8 were active as well as soon as precursor came down. So the engineering at the end was far simpler than expected. This result caused a lot of excitement, not only in the scientific community, but also in the media. And this cover from Time magazine from July 2000 gives an example how eagerly people were picking up this new information. This rice could save 1 million kids a year, but already at that time a problem was clearly visible, but protesters believe such genetically modified foods are bad for us and our planet. So in the year 2000, we were starting from 99 on, when we had our proof of concept, to work on a product. We believed, because of the advice of our rice breeding partners in the International Rice Research Institute in the Philippines, that golden rice could be handed out to the farmers in 2002, because that's the time required in such a case with a clear single trait situation with lots of good molecular markers to produce a variety which can be handed out to the farmers. Well, the year 2002 has passed 10 years ago, and golden rice is still not in the hands of the farmers, despite a lot of effort from a lot of people, despite of generous financial support. And to give you the message right now, it will take until end of 2013 or beginning of 2014 until finally this rice, which has the potential to save a lot of misery, will be in the hands of the farmers. The protesters were a problem and are still a problem, but they were not the outstanding problem. The outstanding problem is, and Mark has already indicated to you, this problem is regulation, GMO regulation. The rules and regulations which have been set up by our society for the work and use of transgenic plants. These regulations are the only cause for a delay of the deployment of golden rice for 12 years. Well, by the year 2008, Science, who had published our proof of concept work, was asking, well, where is golden rice? And I have heard this question many, many times. What happened to golden rice? It looked so promising long ago. Where is it? Why is it not in use? Why is it not in the hands of the farmers? And Martin Ensering came to discuss with me the situation with golden rice, and he wrote an article, Tough Lessons from Golden Rice. It was supposed to prevent blindness and death from vitamin A deficiency in millions of children, but almost a decade after its invention, golden rice is still stuck in the laboratory. And I will show you why. Let me first explain to you how golden rice will reduce vitamin A malnutrition. To understand this, you have to understand the dietary situation of poor people in rice-depending societies, This example here is from Bangladesh. You see a scale from 0 to 140, which this is the recommended daily nutrient intake from the WHO for vitamin A. Fortunately, 100% is a luxurious recommendation for the West. The US Medical Council has clearly established that if people have 50% of these recommendations, they are protected. But because of the poor diet people are eating, where 80% of their calories is coming from rice and only the rest from fish and fowl and vegetable, and where fruit and vegetables are providing provitamin A and fish and fowl vitamin A in red, women don't even reach 50%, they have 40%, and children don't even reach 30%. So the idea would be to provide with the rice part of the diet so much provitamin A that women and children get across the border of 50%. And that's not at all a problem with the rice varieties which will be handed out to the farmers in a few years from now. Even golden rice varieties with a modest content of provitamin A of 2 micrograms would bring with the normal daily diet of rice people are eating, both women and children, across the critical border. So people don't have to change anything but to shift from white rice to golden rice, and as 40 grams of rice per day will provide enough provitamin A, they can even eat the maximum of their rice diet as white rice and add a little bit of yellow rice to be protected. So 40 grams of rice per day would be sufficient to prevent blindness and death because of a disturbed immune system. The average amount of rice children in Bangladesh are consuming is between 200 to 300 grams and women between 300 to 400 grams. Let me make a quick side remark about Greenpeace. Greenpeace has over the years tried again and again to interfere with the development of golden rice, and one of their most successful campaigns was a publication widely distributed of a child sitting in front of a mound of rice, claiming that to have a positive effect, this child would have to eat 9 kilograms of rice per day. And this, of course, showed to everybody immediately that this idea of golden rice is an absolutely crazy idea and not worth any further support. And this had immediately a lot of negative effects on fundraising for our project. So not 9 kilograms of rice per day, but 40 grams is the amount people have to eat. How will golden rice reach the needy? Fortunately, after 12 years of intensive work, rice will reach the farmer soon. It will not replace, but it will complement traditional interventions. It is, however, far more cost-effective than any other possible intervention, and therefore it's more sustainable. The trade is in the seed. Once a variety has been developed, there are no further recurrent costs. So the entire technology goes with the seed into the hands of the farmers, and there are no costs for intellectual property right or patents or any other rights. Because we are talking about a humanitarian project, all intellectual property involved in this entire development is free because we have free licenses for all technology involved for this project. Seeds of agronomically optimized, locally adapted golden rice varieties will be provided to the farmer free of charge and limitations within the framework of our humanitarian project. The farmer will use part of the harvest for the next sowing, and the farmer doesn't require any additional input. Our partner institutions in those countries in where we develop golden rice know that farmers grow a crop only if they have the benefit from it. So the farmer needs additional agronomic arguments to grow golden rice, and that's why golden rice will come with additional attractive agronomic traits like improved resistance to diseases and improved yield. Our collaborators are professional rice breeders, and they know how to do their job. Where is golden rice being distributed? Nowhere. It did not reach the farmer yet. The timeline in the moment is that we expect that golden rice will start to be distributed in the Philippines in December 2013. Maybe it will take a few months longer. Followed by Bangladesh 2014, India and Vietnam in 2015, China and Indonesia in 2016. That's the timeline in the moment, according to the progress in the development of the local varieties and the foreseeable reaction of the national biosafety authorities. Well, there are many further countries which would benefit from golden rice in Asia, in Africa, Latin America. We are slowly working our way into other countries as well, and very high up on my priority list would be Myanmar and Laos and Cambodia, because these are countries with enormous high rice consumption and very, very high vitamin A deficiency. And we will also start to consider working in a few African countries, and I have learned that even Egypt may benefit from the use of golden rice. But all this needs, of course, financial support, and we have to go step by step. We cannot provide the technology to all countries at the same time, but definitely this technology is free, and if we get a request from any government, we are very, very open for discussion, for collaboration. How long did it take to develop golden rice? Well, you know already, it took 9 years to engineer the pathway into the endosperm. Proof of concept was ready in February 1999. How long did it take to get it out to the people? You know already now also. It took actually 14 years from proof of concept onwards. And as I indicated already, it took 11 years longer than it would have taken if we would not talk about a GMO. But unfortunately, vitamin A rice is only possible with the help of GMO technology. So what were the major problems which delayed the deployment for so long? We had to develop a regulatory clean and agronomic attractive variety. Agronomic attractive, we would have done anyhow, but to develop a regulatory clean variety took 10 years. You will not understand immediately what it means to develop a regulatory clean variety. A regulatory clean variety is a variety which fulfills all the molecular and biochemical and genetic requirements established by the regulatory framework. And this is an enormous task because you cannot do it deliberately. You have to work in large numbers. And the problem is that the regulatory conditions do not allow you to work with large numbers because you are not allowed to work in the field. Plant breeders are used to use the power of large numbers to find something new. If you are forced to do plant breeding in a phytotone, that's just impossible. And there are many, many more problems. I will show you a list in a moment. The collection of the data for the regulatory requirement itself requires more than 6 years of very intensive laboratory work. And because golden rice is not a normal variety, but a GMO variety, we have to invest heavily in social marketing. It is not sufficient to give a handful of golden rice seeds to the farmer. You have to prepare the entire country and many stakeholders on what's coming and for what it is good. Here are a few examples on how the conditions for work with transgenic plants delayed the work. We had to delete the electoral marker gene. It is, from the scientific point of view, a nuisance. There are numerous publications which have clearly demonstrated that the presence of a electoral marker gene, as is used necessarily by this technology, is of no potential harm to anybody, but regulators insist that you delete it, and this is possible if you have prepared your experiment for it, but it takes a lot of time. You have to screen for streamlined integration because regulators accept only a transgenic event which has no additional DNA from anywhere and where you have shown that there is no read-through to both sides, and so on and so on. Molecular requirements which do not contribute in any way to putative safety from this material, but a requirement. And this goes on and on. The most disappointing fact being, thanks to the Cartagena Protocol, that to transfer seed material from one breeding institution to another breeding institution in a different country takes 2 years, because it is so dangerous to transport a few seeds of provitamin A rice from one country to another. Well, if you sum up these years, you get to far more than 12 years, but you can do experiments in parallel, and our practical experience was it took us 11 years longer than normally required, and was not unimportant. All this requires a lot of funding. Whereas the total costs for the entire scientific experiment, including 2 working groups, my laboratory and that of Peter Bayer in Freiburg, over 9 years was a total of $2.4 million. The costs for the product development and deregulation is 10 times higher. How do we see the future of biofortified crops? Golden rice was the first example of biofortification. What means biofortification? Biofortification is a new concept, and actually our project developed this concept in reality, to use the power of genetics to improve the micronutrient content of crop plants. We have the potential of genetics. As Mark indicated to you, we as scientists feel the responsibility of using our potential for social and public good. So biofortification is a natural consequence of the growing scientific potential we have in our hands, and the World Food Research Institute has established once that to use biofortification is the most intelligent way of trying to improve undernutrition worldwide. So How do we see the future of biofortification? Well, golden rice was followed in my laboratory already by iron, high iron. We realized that iron is an even bigger problem. There is iron and zinc, there's vitamin B and vitamin E and folate, and there's high-quality protein supplying essential amino acids like arginine, histidine, isoleucine, leucine, lysine, methionine, phenylalanine, threonine, tryptophan, and so on. So colleagues around the world are trying to use this concept to improve crop plants with regard to missing micronutrients. And fortunately, there is some funding for these projects, and there are two consortia working on biofortification. There's the Grand Challenges in Global Health, which is funded by the Gates Foundation, and the Harvest Plus program, which has Gates Foundation and other funding. And these two international consortia of scientists collaborate to introduce provitamin A and iron and zinc and high-quality protein into rice and sorghum and cassava and banana and into maize and wheat and sweet potato and beans. The Harvest Plus program tries to do this as far as ever possible without genetic engineering. The Grand Challenges Global Health program is allowed to use genetic engineering. It is already visible by now that the Harvest Plus program will not be able to provide enough iron if they do not use genetic engineering. The natural variation with regard to iron is not good enough to provide enough iron. The situation with zinc is different. Well, why is so much effort in trying to increase micronutrient content? We have the present situation that micronutrient deficiency takes a daily toll, daily toll of 24,000 lives. And we believe, with our knowledge we have and the technology we have, that all these lives could be saved if we could work unrestricted by regulations. So far there is funding, but it is already clear by now that even projects which have received Gates funding in the area of Grand Challenges and have made fantastic progress in sorghum and cassava and banana will find difficult to receive enough financial support for product development. So the funding was so far good for very good basic research, proof of concept, but it is not clear in the moment from where the money for product development and deregulation will come from. What are the lessons learned from our project? Well, there is no question that biofortification has a fantastic potential for effective and sustained interventions against public health problems like micronutrient deficiency or the hidden hunger. And GMO technology can substantially contribute to streamlined solutions, and you know now a little bit about the project of golden rice. GMO regulation delays use of GMO-based products for more than 10 years and carries a huge financial burden. The time and costs for delivery of a GMO product to the market are so immense that no public institution, nor any small or medium-sized private enterprise can afford the necessary investment in personnel or funds. Just imagine what this means. This means that public institutions which have the natural responsibility to work for public good cannot afford to work on public good because the costs of regulation prevented. Regulation prevents public institutions to work for public good in the area of micronutrient deficiency. Numerous public GMO projects, including many from developing countries and with orphan crops, will not make it to the marketplace under these conditions. If we do not change regulation, a lot of scientific work and investment will be lost. The damage to life and welfare is enormous and affects the poor, and not the rich Western societies which are responsible for this GMO regulation hysteria. You are suffering, not those people in Germany or Switzerland or France or wherever in Europe who are supporting this situation. There is no scientific justification for the worldwide established GMO-specific regulatory system based on the concept of extreme precautionary principle. And there is, to the contrary, a moral imperative to make the technology available for public good, such as nutrition security. But this requires changing regulation from ideology-based regulation of technology to science-based regulation of trades. There is something else important. Effective use requires also that the public health community recognizes that micronutrient-dense food is a cost-effective and sustained intervention against micronutrient malnutrition. The science community is not ready yet to understand this. As I told you, 40 grams of golden rice a day can save life and sight. The future only will show whether Greenpeace et al. Will be able to prevent it. And Greenpeace is determined to prevent it. They have stated it often enough. And I'm certainly experienced enough not to underestimate the power of Greenpeace. Greenpeace it's not only Greenpeace. Greenpeace is the front runner in media, but there are hundreds of comparable NGOs. These are the et al. They have acquired an impressive political power and financial resources. The financial resources for anti-GMO campaigns per year amount to more than 2 billion euros. 2 billion euros. An enormous financial capacity. Greenpeace et al. Are determined to prevent that golden rice reaches those whose eyesight and life could be saved, for no other reason but for the fact that golden rice is a GMO. Greenpeace and many others have decided they maintain their radical ideology-based position. And these ideology-based anti-GMO campaigns are an extreme burden on an effective exploitation of the potential of science we have already in hand for the interest of public good. A last comment. All these organizations are exempt from tax money. They don't pay any tax for their resources because they are assumed to work in the interest of public good. Well, I dare to doubt that somebody who prevents the exploitation of science for public good can be seen as an organization working in the interest of public good. Thank you for your attention.
I just like to remind you that we started 10 minutes late than expected, then we are not yet away from our timing. Thank you very much for our two speakers for their wisdom and the passion of Ingo to just to portray to everybody that science sometimes can be prevented to reach the target, which are the human being, particularly the poor. I think we can have a couple of questions from the floor before we break for this session. Yes, please, you can use the microphone.
Hello, my name is Ahmed Khaled and I'm a medical student in my final year, Faculty of Medicine in Shams University. Really, I'm totally pro-science, but I'm really against giving a group of people the power to do anything without regulation and monitoring. So I would like to question what is really bad about regulations on GMOs. There are regulations on new pharmaceuticals that prevent new pharmaceuticals from getting into the market for 10 years. And these prevent us from getting pharmaceuticals with very dangerous adverse effects. And if regulations on GMOs would prevent something similar to happen for GMOs, so why they are bad? I am really with them, but I would like to ask if regulations are bad or not. Thank you.
Okay, please, Dr. Potrikis.
Okay. Even in the area of pharmaceuticals, the damage by regulations is far bigger than the possible benefit by preventing that pharmaceuticals are used which are not 1000% safe. But in the case of transgenic plants, there is absolute 100% safe scientific evidence that to regulate a technology doesn't make sense at all. If you want to regulate something to be safe for from any hazard or negative consequence, you have to regulate the trade and not the technology. And that's exactly what we request. And that's what the scientific community requests. It does not make sense to single out transgenic plants where we have fantastic scientific proof that they have not presented any risk anywhere, neither hypothetically nor in practice.
Thank you. Yeah, maybe stress that the GMO is a process, is a technology, is not a product. And the product is the plant, and that's exactly, you can show all the variation there is in plants that you cross and that we have been eating for 10,000 years each time with some alterations.
Well, also it's the matter of substantial equivalence that has been critically, exercised, and there are no differences. But again, it is, as you rightly said, with passion, the campaign. I take Dr. Salah and then the question here. Thank you.
Well, my name is Salah Salman. I'm from Alexandria University. Dr. Potrikis, I saw you some 10 years ago here in Bibliotheca Alexandrina when we started to talk about biotechnology in this institution. And I can see and noticed a changing point. Now you are switching from the real enemy of science to some other group of scientists who regulate new products, new materials, new any action, and those are the risk assessors who are leading the regulatory intention. If it's for the public sake, it should stay in the public domain. I mean, if the golden rice is for the public, then there are some institutions like IR4 in the United States who help in doing regulation for those very important products for who needs them. So I think I'm just very critical about changing and switching from the real enemies, the anti-scientific innovation, to the regulators. Thank you very much.
Well, I am not sure whether I understood your comments for acoustical reasons.
Yeah, I can maybe reflect on this, Dr. Potrikis.
Can you help me to understand?
Sure. Well, Dr. Salah actually is referring to You have been doing good science for good years, and he saw you the last time that you are really involved 100% in new science. Now, scientists are dragged out of their laboratory to try and address regulatory issues that took like 14 years. And this is, I think, in his opinion, would be unfair.
Well, thank you for this comment, because it gives me an opportunity to say something which is at my heart. As I indicated and as Mark indicated, good science is important, but good science doesn't solve problems. Yeah. To solve problems, you have to go out of the ivory tower. You have to make your hands dirty. You have to learn how to produce a product, and you have to learn how to bring the product through the regulatory system. If I would not have done what I have done, golden rice would never have been developed, because nobody could invest the money from industry, because there is even proof for this statement, because Syngenta tried to develop a commercial golden rice and gave up after 2 years because the chances for recovering the investment were just zero. So if I would not have, as an academic member, stepped out of the ivory tower and have worked for 14 years on what I'm doing since that time, there would be no golden rice to be distributed to children. So we would have had a nice academic, pleasing result, but this would have been, and that's not how I understand the social responsibility of science.
Thank you. We'll take the last question.
Peter Lackman from Cambridge. I've been campaigning on the questions of regulations for many years. Regulation, whether it's of drugs or of foods, in theory, is there to maximize benefit and to minimize risk and to maintain a balance between these two. In fact, that is a total myth. Sometimes regulation, as in the case of GM foods, has been dominated by those who wish to ban these products, and having failed to ban them, use hyper-regulation as a substitute for banning. That's also seen with the use of animals in research, for example, and to some extent with vaccines. In the case of drugs, which somebody has mentioned, the regulatory system has become insanely overprotective as a result of occasional serious accidents. The current regime on drug regulation is the consequence of the thalidomide disaster about 40 or 50 years ago. That harmed and was totally wrong and was very badly done about 2,000 or 3,000 children. The consequences of this has probably killed hundreds of thousands or millions of people, because drugs cannot be developed, because a regulatory environment has been developed which is so restrictive that the development of drugs has become so expensive that they can only be developed either for diseases that are so common that you can make blockbusters, or that are so rare that they're exempt from the regulations. And the consequence of this is wholly harmful. The FDA behave the way they do because they're terrified of being telephoned by congressmen before breakfast every day. There is no sense in this system, and I do believe that it is starting to change, that those people, the drug industry itself now realizes that this is unsustainable, and Ingo is entirely right. Until we actually have a proper cost and risk-benefit analysis of what regulation should do, we're headed for total disaster, both for drugs, GMOs, use of animals, vaccines, and everything else. Stand up and be counted.
Thank you for your remarkable. I'll take from our young fellow here the last two questions, and then we break. Thank you.
Yes, thank you so much, Dr. Patrikos. Actually, your presentation has been so great, it has particularly sent me pensive. My question, actually, I will begin with a comment. Because the promotion of GMO products has faced a very stiff resistance, especially from...
Can we get to the question, please? Because we are really running late in time.
Right. Yeah. So my question is, what mechanisms has the scientific community prepared themselves with, or rather put forward, to counter these tenacious, especially decision makers who misinform the public, the uninformed farmers, of course, for them, they do not have a problem, but the less informed people who are taking the podium to deform them and deny them the right to save lives. What mechanisms shall we take, or you've taken, to ensure that this can, in the long run, be solved? And secondly, the priority for promotion of golden rice, I think it is in Southeast Asia, that's where it is starting. Or, in my own personal appeal, could it be also possible to consider developing part of Africa, or rather this part of the world, to come in as fast as possible, because this is a very, very important project that has to be taken into consideration very soon than later.
Okay. Please.
I'm sorry, I need the help of the chairman again. The acoustic is for my 78-year-old ears too weak here.
Yeah, and this is also, the question has been really dragging. Your intention, I had also the same problem, actually. Your question is around the possibility of getting this technology to Africa?
Yes, and also which measures are being taken to to get a breakthrough through the resistance that exists?
Yeah.
Okay, the answer is simple. This technology will come to Africa soon.
Yeah. And then maybe over a coffee break, we can maybe have a chat with Dr. Ingo Potrikos on this. Okay. Thank you. Well, I'd like to thank you very much for attending this session, and please join me in thanking our two eminent speakers for their intervention today.